Okay, so now we're going to skip forward to section 10.7. Section 10.7 is going to look at spur gear kinematics. Now, again, kinematics is the study of motion without regard to any forces. So we're going to look now more specifically at when we have two gears that are in mesh with one another. How are they reacting to each other rotationally, if you would? So, one of the terms that we refer to this relative motion between the two gears that are in mesh with one another is called velocity ratio. And the variable that we use for that is capital V, capital R, velocity ratio. And velocity ratio is going to be the ratio of the angular speeds between the gear and the pinion. So to calculate this, if we go underneath our camera to page 273, and the bottom half here is this section that we're looking at on the PowerPoint. It's 10.7 spur gear kinematics. And the equation for velocity ratio is simply going to be the angular velocity of the driver, which is the higher speed um, uh, gear, divided by the rotational speed or the angular speed of the gear. So this is going to be another equation that we want to add to our equation sheet. So here's our equation sheet. I'm just going to go right down here. We're going to say velocity ratio is going to be equal to angular velocity of our pinion divided by the angular velocity of our gear. Okay. Now, those are the differences between the rotational speeds. Now, many times we know, what's coming in and what's going out or what we're trying to achieve. And when we look at velocity ratio, so I'll write this over here on the side. Not ration, ratio. Okay. Velocity ratio. If we just kind of look at this first version of how to calculate it, taking the angular velocity of the pinion or the driver divided by the angular velocity of the gear or the driven gear. Remember, this is two gears that are in mesh. And it's really just looking at the ratio of the angular velocity. Each one of these is going to have, for instance, RPMs on top, RPMs on the bottom. So velocity ratio is a truly dimensionless variable. Okay, so there are no dimensions related to this because they cancel out. RPMs are going to cancel out on top to bottom. Now, not only can we look at the rotational speed or the angular velocity of each one of the gears, we can also look at their physical sizes. Okay, so we can say it's also going to be equal to the pitch diameter of the gear, number two has to go on top here, divided by the pitch diameter of the pinion. Okay. The top value is always going to be the larger quantity. So when it's speed, the pinion speed is going to be a higher speed. Okay, again, think of that motor coming in and we want to reduce it to be usable for the output or the gear. Okay, but when we're looking at physical size, the gear is always going to be larger than the pinion. So that's why the two is on top here. We can also count the number of teeth. So we can say the number of teeth on the gear divided by the number of teeth on the pinion. Okay. Now we can't do diametral pitch because diametral pitch size of the teeth is going to be the same, right? So that's not going to work for us. But if we know radiuses, that will also help us out too. Okay, which would just be half of the diameters. Okay. So the only ones here that we don't have identified over on the right-hand side here yet are going to be our angular velocities. Or angular speed, right? And those units are going to be RPMs or radians per second, right? Radians per second. Now, again, velocity ratio is exactly that. What is the angular velocity? What is the rotational speed ratio between the input to the output? Okay, from the input to the output. And again, we can use the angular velocities themselves or the physical sizes, diameters, number of teeth, or the radiuses of the actual gear set itself, if we know that. Okay. Now, Another relationship that we have that is going to be familiar because we just saw this in Module 4 is when we start looking at the rotational speed of the gear or the pinion. Okay. First of all, when they are meshed, I want to kind of show this because we see this on this particular illustration. Notice that the direction of rotation for each of the gears is opposite. Okay. And it makes sense because when this is in engagement, we're going to push past this way, which means this one is going to go in this direction. Okay. But now at the very end there, we not only have rotational speed on each one of our gears, we have straight line velocity. This is called pitch line speed. Pitch line speed. Okay. So pitch line speed, we turn the page, is going to use the variable lowercase v sub t. So tangential straight line velocity, okay, is going to be equal to the radius from the center of rotation times the angular velocity of that gear. So if we're working with, for instance, pinions, we're going to use the radius of the pinion times its rotational speed. If we're working with the gear, we're going to take its radius, which would be larger, times its angular velocity or its W. Okay, so those have to be meshed. So if we look back at the illustration, if we're calculating for pitch line speed, which would be the straight line velocity component here, we have to work with the same values. So if we're on the pinion side, it has to be the pinion radius times the angular velocity of the pinion. If we're on the gear side, it has to be the radius of the gear times its angular velocity. We can't mix and match. We can't use W1 and R2. Okay. So make sure. Now, let's kind of look at this because some of it looks familiar, but it's really a reapplication of what we saw previous. So for instance, I'm going to draw down here a frame member. Okay. And I'm going to draw a radius, and it's going to kind of mimic our gear right here. All right. I'm going to draw a radius to where that pitch diameter is. Okay. And if I know that the angular velocity of that link, so instead of drawing the full circle, we're just drawing the radius here. And if the center of rotation is a frame, it doesn't move. And the radius or the gear itself is a link, 1 and 2, this would be the angular velocity of link number 2. See? So this is a simplified version of from the center of rotation here to the point of engagement. Now, from that point, we then are going to have straight line velocity, right? And that's going to be what we call tangential. And the only reason we call it tangential is because this would be going around in a circle and it's tangent to the radius back to the center of rotation. So it's going to be 90 degrees, just like in Module 4, okay? Now, this relationship here is going to be dependent on how far away our point is, the end point is from the center of rotation. So straight line velocity, what we call pitch line speed, because this is the pitch diameter, this is the straight line velocity, is going to be equal to W2 times R2. If we're on the pinion, it can also be equal to W1, which is the angular velocity of the pinion, times the radius, which is the of the pinion. Does that make sense to everybody? So whether it's a 1 or 2 is really gear or pinion. Okay. So this is familiar to us. Now, the thing we have to keep in mind here, though, is when we are dealing with this equation, just like in Module 4, these units have to be in radians per second. They cannot be in RPMs. Remember, in and out of this equation, our angular velocity is in radians per second, okay? And then pitch line speed, VT, Its units are going to be inches per second. Okay, so distance divided by time, because we're going to have radians per second here times inches. So inches per second. Okay, make sure I have all that. Questions on this? This is kind of a repeat. This is a reapplication of what we actually learned back in module 4. Module 4, because we're module 5 now. Okay. All right. So that is what we see here. Now, let's look at example 810. Let's do this together. So I go underneath and I turn the page here. Example 10.8 is at the middle of page 273. Now we're going to be determining the speed of some mating gears in RPMs and calculate their pitch line velocity. Okay. We're going to first identify what variables are given, what we need to calculate, identify any equations that we have available that'll help us, and then kind of work through the steps. Okay. So I'm going to go underneath here. This is our example. Okay. So we have here a set of gears right here that are used to reduce the speed of an electric motor, which is at the bottom here, 1800 RPMs. It's going pretty fast. Okay. That drives a grocery checkout conveyor. So here's the conveyor itself. So notice that our input is the electric motor. It's engaged with the gears on what would be the same center line as the conveyor. So the speed that this gear is going around is going to be the same speed as the conveyor itself. It says the gear on the motor down here is a 10 pitch pinion. Okay. Has 15 teeth and drives at 1800 RPMs clockwise, as we see identified in that diagram. They want us to determine the speed of the mating gear, which has 45 teeth. Also calculate the pitch line velocity. Okay, so a lot of words here. Now we got to figure out what we know and what we need to find. Okay, so first of all, the set of gears are going to reduce the speed of an electric motor. The gear on the motor shaft is a 10 pitch pinion. 10 pitch is the diametral pitch, not the pitch diameter, 10 pitch. So, for example, 10.8, I'm going to zoom out just a little bit. We're given the diametral pitch. And this is going to be, even though it says for the pinion, because the pinion is engaged with the gear, they both are going to have the same diametral pitch. And it said it's a 10 pitch. So it's diametral pitch of 10. And we know that to be teeth per inch. Okay. It also says that the pinion has 15 teeth. So we know that N1, we'll call the pinion, number 1 is always pinions. We know that's 15 teeth. Okay. And drives at 1800 RPM. So that's going to be W1 is 1800 RPM. Oops, go down here so you can see all of it. Okay. Moving along, determine the speed of the mating gear, which has 45 teeth. So I'm going to say, all right, N2, which is the mating gear, is 45 teeth. Okay. And we need to determine the speed of the mating gear. So we need to, is that all? We have everything else? Yeah. So we need to find W2. Okay, so that's the angular velocity of the mating gear. So we know what the input is on the motor. We need to find out how fast is W2 going on that gear that's mounted to the conveyor itself. Okay. All right. Now, what we're given, we have the diametral pitch. We have our number of teeth on our pinion and on our gear, and we have W1. Okay, now we need to find W2. if we go back to our gear equations, okay, we have this velocity ratio here. Now, we don't always have to calculate velocity ratio with this. We can take this and all of these quantities are equal to each other. Now, we need to find a W2, right? We know W1, so I'm going to put a little check mark by W1. And if we set that equal to not the diameter, but instead the number of teeth, we know N2 and N1. Do you see that? So I can set these two equal to each other and solve for W2. You see that? So I'm gonna go back over here. Oh, it says also calculate the pitch line velocity. So we also need this. Sorry, I thought there was one other thing. There we go. So just add that in because that'll be our second part. So to find W2, we're going to take our first equation, W1 divided by W2 is equal to N2 over N1. Make sure you get the right things in here. The tops are always going to be the larger value of whatever the ratio is, and the top to bottom have to be the same variables. Now, for this one, like I said, we know W1, N1, and N2. We need to find W2. So rearrange this equation to solve for W2. Okay. Should get something like this. Okay. And then go ahead and put your values in. Now, for this equation, we do not have to put this into radians per second. We will for this one when we do this one. But here, remember, this is just a ratio, and we want to know, we always want to report out our angular velocities in RPMs. You should get a value of 600 RPMs. Everybody get that?
Yes.
Okay, great. Thank you, Garrett. Make sure that as you're doing this, that you're writing out your equations in variable forms clearly, putting in your values with your units, cancel things out so that when the final units aren't canceled, that they're coming out to what you're expecting. And then also make sure that you say W2 is equal to. Don't just put a box around 600 RPMs, okay? All right, so that's the first part. So that's W2 is going to be at 600 RPMs, all right? Now, this is an extra step that I'm doing, all right? And so the problem isn't asking this, but let's calculate the velocity ratio. Now that we know what W2 is, we can calculate what that's going to be. And remember, the velocity ratio is telling us how many times does our pinion have to go around in order to get our gear to go around once. So we're going to add velocity ratio is going to be equal to W1 divided by W2. We know that our W1 is 1800 RPMs and our W2 is 600 RPMs. So RPMs cancel out, which we're expecting. Velocity ratio is always going to be unitless. So if I take 1800 divided by 600, we're going to get 3, and that's it. No units here. They cancel out top to bottom. Now, what this tells me is that my pinion, okay, so if I look on here, my motor has to go around 3 times in order to get this to go around just once, my output gear, okay? So that's a 3-to-1 ratio. Now, again, it didn't ask for this, but I'm going to be looking for this to make sure that you do it. It's just kind of a logical thing to do right now, kind of natural. All right, then the second thing that they are looking for is what is the pitch line velocity, okay? So again, what that's going to be is if we go back over here, that's going to be looking at one of those gears, whether it's the pinion or the gear, and looking at how fast it's going around and what this VT is going to be, okay? So, oh, I'm sorry, I'll come back here. VT is going to be equal to the angular velocity of the length that we're looking at, and then how far away from its center of rotation that endpoint actually is. If I'm looking at the gear or I'm looking at the pinion, I have to use consistent units here. So VT, okay. So when we look at this, what do we want to use? Do we want to use the pinion or do we want to use the gear? It doesn't matter. They're both going to have the same pitch line velocity because they mesh together.
Gear.
You want to use the gear? Sure, we can use the gear. So if we go here, we're going to put 2's for each one of these because they're the gear. So here, my angular velocity of my gear is going to be 600 RPMs, right? So I'm going to put 600 RPMs here. And then I'm going to multiply by the radius 2, right? Is that correct?
No.
Why is it not correct?
Wrong units.
The wrong units, exactly. Remember, in and out of this equation, and I think we have that right here, we need radians per second, right? So number one, we have to convert W2, the 600 RPMs, to radians per second. So luckily I used pencil, okay? And I want to erase that. So over here, I'm going to do my W2. So I know that I have 600 revolutions per minute. 1 revolution, 2 pi radians, revolutions cancel, and then I've got 1 minute, 60 seconds, minutes cancel. So across the top, divide by the bottom, my W2 62.83. Anybody else get that same value? I only did it once. I could be wrong.
I got the same one.
You
62.
did? Okay, excellent. Okay. So now we're going to use this value, 62.83, over here. Okay. So this is going to be 62.83 radians per second. Okay. That's going to be my W2, right? Now, radius 2. So the radius of my gear, if I go to my problem, it did not give me the radius of my gear, did it? It gave me the number of teeth. And then I also know that it is a 10 pitch pinion, don't I? So what I need to do is I need to calculate the pitch diameter and divide that by 2. Okay. So using the number of teeth on the gear and the diametral pitch, I can get the diameter of the gear, but then divide by 2 for the radius. Does that make sense? So over here, I'm going to do that work down here. So if I rearrange, and I'm going to do it right here, solving for the lowercase d here, d is going to be equal to number of teeth divided by diametral pitch. So D2 is going to be equal to N2 divided by the diametral pitch, which is, was it 45 teeth? Yeah, 45 teeth. Remember, divided by 10 teeth per inch for the diametral pitch. Teeth cancel. And my pitch diameter is going to be 4.5 inches, right? 45 divided by 10. So then my R2 is going to be 2.25 inches, right? Everybody get that same value? So the R2 is what we're going to put right here. So this is going to be 2.25 inches. So my straight line velocity or my pitch line speed, 62.83, 2.25. So radians times inches is going to be inches per second, 141.37 inches per second. Did you guys get that same number?
Yep.
Okay. Now, for some reason, when they did theirs, if we look, they did in inches per minute, but then they put it into feet per minute. Okay, so let's go ahead and just convert this into feet per minute to make sure we get the same value, which we should. 141.37 inches per second. And I know that there are 12 inches in 1 foot. So the inches go on the bottom here. Inches cancel. Now I'm in feet per second. And now seconds. I know that there's 60 seconds in 1 minute. So seconds cancel and I end up with feet per minute. So if I multiply that out, 141.37 times 60 divided by 12, my, straight line velocity or my pitch line speed is going to be 706.9. Oh, right on the money. Feet per minute. That's my final answer. And unless it says to put it in final units of, okay, you could leave it at inches per second. They happen to do it in feet per minute. So we'll just be consistent with what they had to be sure that our answer matches. So that is going to be then the straight line velocity component of the end point or the end point of the radius of that gear. If you would, each one of the teeth is that value. Okay. And then that takes care of what they were looking for our problem. So the first thing they wanted was how fast is the conveyor going, which is attached to our gear, 600 RPMs. We added the velocity ratio of 3, and that just means that our pinion goes around 3 times when the gear goes around once. And then the third thing that we calculated here is the pitch line velocity, and that is 706.9 feet per minute. Okay. All right. Any questions on that problem? Okay. If not, I'm kind of looking at the time here. We have a couple more examples to go through, but I'm going to save those for the next time we're together. This is a good place to kind of stop for the day, looking at the time, and then it's a new subject that we're going to get to. But before I let you go, let's take a peek at our assignment to see if there's anything that you can work on, which I know there is. And before we do, let's just peek at the practice problems. So we did, it looks like the first 3 here. Okay, so we'll have 4 to do the next time we're together, which will be perfect. And then if we look at assignment number 5, the problems that you can work, you can do all of the problems through 1016. Now notice that I have some notes here. For 9, 13, and 14, the problem statement says internal gears. I only want you to worry about external gears, okay? So both gears are external, so they're going to be utilizing the equations that we focused on in our lecture here today. So let's go to the end of the chapter and just go over, just kind of point out what you're going to be doing for these problems. So the problem set starts on page 295. And the first problem that you're going to do is going to be, hold on here. It's going to be 10.5 and 10.6, and you're only doing part A. Okay, so you're only finding the center distance, so C, for the descriptions that we see here. Okay, so just center distance. So if we look back over here, you're just doing 5A and 6A, all right? So just center distance. Then if we jump up over here, this is 9, 13, and 14, okay? You're going to do both parts A and B. So it's the pitch diameters, which is going to be the lowercase d, and the center distance for these three problems, and treat these all as external gears. They are not, no internals. They're both externals as they come together, just like the ones that we did in our examples. So it looks like you're given some diametral pitches, number of teeth, and again, both externals. Don't worry if it says internal. Okay. And then you're going to calculate the pitch diameter and the center distance between those two gears. And then the last two problems are going to be like the last problem that we looked at. So 15 and 16, you're going to find the speed of the gear, which is going to be W, and then the pitch line velocity, which is going to be VT, with the descriptions that are here, which are consistent with the last problem that we just looked at, which would be example problem 10.8. Okay, then after that, we haven't covered yet. So, so like I said, if you wanted to get started on the beginning of the assignment, you would have quite a few that you could work on. Okay, so a little bit over half. The problem answers for this are here. So you're going to notice if you click on that PDF, you will have, if it comes up here, the final answers, just like you have for other modules that we've worked on. So I always expect you, why? I always expect you guys to take a peek at those when before you hand in. That way, you know if you're on the right track as you move along. I can certainly always answer questions, but I think it is kind of nice for you guys to refer to that. So always check that before you hand in. That way you know you're on the right track. So with that, that's all that I was planning on covering today. Does anybody have any questions before I let you go? Okay. Then what I'm going to do is I'm going to stop our recording here.